Hey, this is Christian Calrical for the Physics 2211 Lab 1. So we're going to go over the introduction, models, our experiment, the coding we did for this experiment, our discussion, and then finally our conclusion. So the purpose of this lab is to observe an object moving with constant velocity. These observations can be used to develop a computational model that represents this constant velocity. So the fundamental principles of physics that we used for this model was Newton's first law, Newton's second law, and the idea of constant velocity. Newton's first law describes inertia and explains how our object is going to continue going at a constant speed over time. Then Newton's second law deals with forces and allows us to derive the velocity and position update formulas that are used for these iterative computations. And lastly, constant velocity just means that the net force is zero, which we will prove later. So these are some of the laws that we use. We have Newton's second law, which is F equals ma, which can be used to derive the velocity and position update formulas that we see here. And then here's a little preview of the results that we had. So as you can see, the tracker data, that's our experimental data. The GlowScript data is our computational model. And then the linear trend line of tracker is how we got the data to develop our computational model. So the system and the surroundings here, we have the system, which is the object we choose to observe. That's a spool of thread that we rolled across the ground here for the experiment. And the surroundings, everything outside of the system, including friction, gravity, and whatever else was going on other than the spool of thread. And then to make these observations, we used Tracker for the experimental data and then GlowScript to develop the computational data. So our experimental procedure, we first recorded an object moving at a constant velocity. Then we used Tracker to observe a position versus time relationship for the observed system. Then developed a computational model to represent the observed object based on our physics principles that we decided to use. And then lastly, we compared the Tracker and computational data using Excel. So these are the initial conditions that we developed using the tracker model. As you can see here, the X position for tracker is not exactly at the origin. We started a little bit past there, and that's what we named as the initial position, which was helpful for our computational model. Same thing with the time. The time we didn't start it at 0 seconds on the video. And we picked a time that was in our time frame that we wanted for our observed system. And then we know from our prior knowledge that the tracker uses a 30 frames per second ratio, which is equal to 0.033 seconds per data point that it has here on this model. As you can see here, it goes up by about 0.04, but really the delta t is 0.033. And then lastly, the trend line of the tracker data, we had a slope of 0.0127, but really that is in the units of meters per frame, and we want this in meters per second. So if we multiply this by the known value of 30 frames per second, we can get 0.381 meters per second. And then putting these initial conditions into GlowScript, we could put the initial position, the initial time we use, our delta t that we use using known data, and then our velocity, which technically this is the average velocity, but we know that the average velocity is equal to the final velocity when we have constant motion. So that's what we put in for our ball velocity. And then we applied these physics principles of velocity update and position update formula in our computational model. As you can see, we didn't actually update the velocity because the velocity wasn't changing. And then the ball's position, we updated that using the velocity and the change in time. So this is what we got with our computational results. And as you can see here, the lines for the GlowScript and tracker data are very similar, showing that the computational model represented our tracker data very well. And then here is just a model of how the ball rolled using our computational model. So some possible sources for error. There could have been forces acting on the object, such as friction or air resistance, and then we could have possibly had an imprecise tracker measurement. So what if, and what does this mean? What if the axes were flipped? This would cause the position of the spool to be moving in the negative direction. This means that the slope of the graph would instead be negative, but in this case, velocity would still be constant. And this means that if velocity is constant, we have zero net force. However, we cannot exactly predict what these forces are, or at least their magnitude, because we know that there's going to be friction force used to push, and then the force used to push the spool initially, but we don't know the exact magnitude of these forces. So we ended up concluding that our experimental results were very similar to our computational model predictions. And because of this, we can assume that we had constant velocity and no net force acting on our object. These observations support Newton's first law.